Hello and welcome to day 7 of our Upward Bound Advanced Math content. Today we're going to start looking at transformations of functions. It is noted as part 1 because we're going to take 2 days on this. I feel like whatever math class you're going to go into next, it's probably important enough to validate having 2 days. So looking at sort of our target for the day, we're going to look at building new functions from old functions. And if you remember back to last time, I think maybe the time before, it was the time before, we looked at just graphing a bunch of different functions, and we're going to use a lot of those in order to create these new functions for us. So if I go ahead and look here and look at getting started, I want to graph y equals x. Now that's not what I want to do. This is a skill from any Algebra 1 type of class, or even below that. But we started looking at, simple linear equations, and this one is, about as simple as it gets because there's nothing happening to the x. So we just know that we get a diagonal line. It goes through 0, 0, and yeah. For the next one here, it says graph y equals x plus 2. And in Algebra 1 classes, we said, okay, well, that has a slope of 1 and a y-intercept of 2. So it goes up 1 and over 1 from 0, 2, and that pattern continues. It could also go backwards, down 1 and left 1, and so on and so forth. I'm going to argue that there's actually a more how do I want to say this? I guess more of an in-depth way that we can look at this, or maybe more of a general way to look at this. And so, what are the what's the same and what's the differences? What different things do we have going on in these two graphs, and what same things? Well, same-wise, we know that we have same slopes. Okay. Now, just having that knowledge and knowing what that means, that actually means a lot more than just one item. We know that they grow at the same rate. We know a lot of things. And then what's different, the differences are, I would say almost their differences are more circumstantial than anything. They're really different everywhere. We're just looking at different points. Okay, but you can you can say those things however you want to. Like, what's different? You could say just the starting point, the y-intercept is different, but that causes everything to be different once you have the same slopes between the two lines. So there's a lot more hidden that's the same and different in these two graphs. Let's use that same idea and graph these two. I would say they're pretty similar. I started with y equals x and then y equals x plus 2. Here I'm looking at y equals x squared and y equals x squared plus 2. I'm going to use a table of values and just a quick one just to see what happens at 0, 1, and 2. You could use a graphing calculator if you wanted to. You could kind of use whatever you want. And I'm also using the fact that this graph is mirrored on both sides of the vertex. So I obviously doing it this way, I know a little bit more about the function x squared than I'm leading on here, but that's okay. So for 0 squared is 0, 1 squared is 1, 2 squared is 4. So I get 0, 0, 1, 1, and 2, 4. And I'm just going to mirror those over here. Now, for the fun part of trying to graph this without looking at it, I am looking at it, but, drawing on a pad is a little bit different. So that's that one. That's all well and good. Let's go ahead and look at this one over here. See what I mean? Sometimes things get a little bit weird. I'm going to use my same points, 0, 1, and 2, and see what we get happening here. Okay. So at 0, 0 squared is 0, plus 2 is 2. 1 squared is 1, plus 2 is 3. And then 2 squared is 4 plus 2 is 6. So I actually get, it's about right there. Okay, it's a little bit off my graph, but that's okay. I'm going to mirror that on this side, make it look the same, and try to graph that parabola. And so we notice that we get a similar graph in the same way that the two lines up above were similar, but they're still different, right? There are differences, and I hate that graph on the right, so I'm going to kind of forget that it's there and go ahead and scroll down. Now let's look at these two. So how is that different from this one right here? Let's do the same thing. I think a table of values is working pretty well for us, maybe seeing these differences. And know that no matter what graph you pick or what function you're trying to graph, you can always do a table of values. I personally love table of values because they help out quite a bit. And this one's going to be a little bit weird, so bear with me here, and we'll try to figure this out. We'll try to kind of find the similarities and the distance between points kind of thing. So let's see what we have. We have 0, and this says 0 plus 2 squared. So that's 2 squared, which is 4. 1 plus 2 is 3, squared is 9. So that's already off my graph. And so this one definitely will be. Maybe we look at, let's see, can I drag these down? I can, that's good. Maybe we look at a couple other points, and maybe we try to find, well, we can do this one. 2 plus 2 is 4, squared is 16. So see, that one's even further off my graph. We got to start seeing where this thing starts coming downwards. Negative 1 plus 2 is 1. Squared is 1. And then negative 2 plus 2 is 0. 0 squared is 0. And let's check negative 3. Negative 3 plus 2 is negative 1. Squared is 1. So that's kind of my turning point right there at negative 2. So I get this point. So it's not mirrored across the y-axis. It's mirrored over here now. So at negative 1, it's 1. At 0, it's 4. And then it goes off my graph. And then these points get mirrored over here. And so I get a graph that looks about like this. And there we go. Let's look at this one. Switch colors again. I'm just going to do another quick table of values. We'll pick 0, 1, and 2 again. We'll see how that works for us. 0 minus 2 is negative 2, squared is 4. 1 minus 2 is negative 1, squared is 1. 2 minus 2 is 0, squared is 0. Let's go, I guess, 3 and 4. Because I'm getting the feeling that this is my turning point, because I always see those 4s and 1s, and that seems to be where I start turning. 3 minus 2 is 1, squared is 1, and 4 minus 2 is 2, squared is 4. All right, so we get that same looking graph over here. A little bit different, but again, similarities and some key, whenever you look at something and the only difference is where the points are, which is kind of what we have going here. That our key difference is just location of points, but all the shapes are the same. That has to mean something important's going on. In fact, it all comes from this one right here. Okay, if I'm looking at this one in black, okay, the way I get the blue one is I just take this one in black, and let's see if I can drag that, and I move it up 2, and then that looks like the blue one. If I take that one in black and move it left 2, then it looks like the red one. And if I take this one in black and move it right 2, that looks like the green one. Okay? With varying degrees of being able to draw a smooth curve, all those fun things. So in all these previous cases, the x squared, the one in black, we call that the parent function. So that is our parent function. All right? That's the one that starts everything. Once we get that one going, then everything kind of falls in place from there. And so really what we worked with is we worked with this general equation that says y equals, in parentheses, x minus h squared plus k. Okay? The h, the one inside the parentheses, meaning these two, what did they do to my parent function x squared, or the black one up above? They moved it left and right. Okay? So the h moves it left and right. And then you can even get even more in depth as to say that when it was negative, so here I see this one's a -2, it moved it right. And that's why there's the minus h in there. Okay? To say that h, as it stands, really just moves it right. Okay? In general, anything that's in here is going to move it left or right. But if that number is positive, if h is a positive number, or if this thing looks like x minus something, then it's going to be moved to the right. Whereas the plus k, that was like the blue one up here, where it said +2, but it was outside of the squared, it moved it upwards. So when that number out there is a plus, it moves it up, and if it were to be a -2 up there, it would drag it down 2 places. So moves it up, moves the function up. Just because I don't think it's here, yeah, I want to write it here. This doesn't just work for x squared. In fact, I would say that that's what was going on in this problem, where I said x plus 2. This is taking the parent function of y equals x and adding 2 on the outside, moving it up 2. Okay? The trick with y equals x is that since nothing's really happening, there is no like inner function, it's just x. There's only so much that can happen. There's only so many ways that you can kind of mess with it, because notice that if I were using the x squared, then these two would not be equal. So this is the one that I gave you right here. How is that different from this one? If I put that +2 inside the function. Well, since it's just x and there's nothing else going on, these two statements right here are the same thing. I don't know what I was trying to do there. I was trying to do this. So these two functions are the same thing. The parentheses don't matter. So just as much as this is like moving it up 2, like from here, moving my parent function up 2, is it not the same as taking this function and moving it left 2, that my +2 would do? That is the same thing. So you can either see on the y equals x parent function, you can either see it, well, I moved it up 2 spaces, and that's fine. Or you could say the +2, think of that as inside the parentheses, and it moves it left 2 spaces. It does the same thing. Okay? So all that to say that it doesn't matter what the function is. It doesn't matter what function you're working with. The real general form, this is a general form of a very specific case of the function being x squared. But in general, if I say that y equals, for us, we're going to say f of x minus h plus k. H controls the, sorry about that, H controls the horizontal, and K controls the vertical change. Okay. So let's go ahead and look at the next page. Sorry, give me a second here. So I want to graph these three functions on the same graph just to see what they look like. We'll do the square root of x in red, and square root of numbers. I know that square root of 1 is 1, square root of 0 is 0, Square root of 4 is 2. And I guess I have square root of 9 is 3 on here as well. So this is our parent function for this example. Okay. If I want to graph the square root of x minus 3, that's just going to move it 3 units right, and it's going to do the same thing. So here's how we kind of take some, use some speed here and some previous knowledge to graph it. I'm moving each one of these, I guess 4 points that I have, moving them 3 units right. So this point is going to move 1, 2, 3 units right. This one, 1, 2, 3 units right. It's kind of hard to see. And then that one's going to end up off my graph. But it's going to sort of match up to that red one. Okay. The next one there, the third one, y equals square root of x minus 3 plus 4. That plus 4 being outside, this is going to move it up 4 spaces. So I can look at this one 2 ways because I've kind of dealt with a building block mentality here. I could either take square root of x, the red one, move it 3 units right and 4 units up, or I can just take this blue one and move it 4 units up and be good to go. So 1, 2, 3, 4. And again, we're starting with the square root graph, and so that one has that weird thing that it really starts at a point. And this one does. It starts right here. Moving this one 4 units up, and then 4 units up. And then, yeah, that last point would be off of our graph. So we get a graph that looks about like that. So that's the green one there. The red one was the original, and blue was the middle. Okay. All right, the other thing that I want to talk about today is reflecting functions, okay, which we can do the same type of way. There's a quick and sort of painless rule for reflecting functions. To graph with a negative on the outside of the function, so that would look like, well, x squared isn't that exciting because it doesn't really change much, but x cubed. So now it doesn't look any different either, does it? Yeah, it kind of takes a weird function for that to really matter. But if we have the negative on the outside of the function, okay, yeah, x squared looks different. Sorry, x squared looks different when you're calculating it, but once you once you find your answers, it's all going to be the same. Because when you're squaring a negative, it's the same thing as well, your points would be flipped over. Sorry. Let me get back to this. With a negative on the outside, it flips it across the x-axis. With a negative on the inside, it flips it across the y-axis. So I guess there is a difference with x squared. If we had y equals negative x squared, like that, we'd be plugging in our points, and instead of getting an upwards U shape, we would actually get a downwards U shape. The difference between that and this one is that no matter what, whenever I square my negative number in here, that's going to turn it from a U shape. And let me kind of darken this side. Not that it really changed. It's still going to be a U shape, same U shape we've seen. It's going to turn it into this. You're just going to get your points sort of from the opposite side. Okay. It's not that exciting. So that's what I was getting at with x squared. But let's look at this square root of x one, because this one is a little bit tricky, right? We had 0, 0, 1, 1, 4, 2, and 9, 3. And we're not going to get all those, but that's okay. So I'm going to graph that parent function really quick. Okay, I'm going to graph it in blue. 1, 1, 4, 2. That's as much as I get on here. So that graph looks like this. And I want to reflect this across the x-axis with that negative being on the outside. And you could use graphing software if you wanted to, either calculator or GeoGebra. That would be just fine. But what we get is we get this graph here. For some reason, graphing it downwards is a little bit more difficult here. Okay, so that's graphing it that way. All right, whereas if I take my original square root of x and I put the negative inside, that reflects it across the y-axis. So this time we're going to reflect it across the y-axis, and it's going to send it this way. And -4, +2. Okay? So that's the difference in where we have some negatives. Okay? All right, so let's try to do some of this. We've got 4 problems here, and I want to do these without any graphing technology. We know that from kind of that day 5 stuff, that x cubed goes through 0, 0, 1, 1, and -1, -1. And then by 2, it's all the way at like 8 and -8. So it's going to kind of look like this. Let me try to smooth it out as best I can. Okay, it's going to look something like this. Now, what does this one do? Right, the negative on the outside, okay, negative f of x, is going to reflect it across the x-axis. So that's going to take this one and reflect it across the x-axis. So whatever was low, whatever was down below becomes up here, and so we get something that looks like this. 0, 0 is always going to reflect back to 0, 0, so it's kind of boring, but it just goes this way now. And we sort of talked about this with our end behavior. This matches up with our end behavior terminology, that when I have a negative leading coefficient, it's going to start high and end low because it's an odd function. Okay, so we're still working with the x cubed. I'm working with the flipped one, the one that I had right here, and the +1. Okay. +1 inside moves the opposite direction. I always think of right and up being positives, but with it being on the inside, the plus actually means to the left. Okay, it means the opposite of what I want it to mean. So, and this is all kind of coming from this red one up here. So we're going to alter the red one, basically move it 1 space to the left. So I'm going to get a point here, point here, point here, and go with my S shape as good as I can. Ooh, I don't like that. Ran into, that's even worse. Get out of there. That's a terrible graph of x cubed, but we're going to go with it. Should be a little more curvature there, but it's really hard to do on this pad. Okay. Then I'm going to take this one, because that's all that this is right here, and I'm going to do this -2 on the outside. -2 drops it down 2 points. Okay, so I'm going to take my new 0, 0, which is that -1, 0, and drop it down 2 points. And I get a point there and a point there. And yeah, that 8 would still be off my graph. So it's going to be really close to this next point, but not quite there. It's going to look something like this. Still going to start high and end low, just like our end behavior says. But yeah, that's what we've got. Okay. Hopefully that helps you. Make sure you get your homework done and catch up on any homeworks that you're still don't have turned in. Okay. We'll see you in class. Have a good day.